Hello. So today, Ryan Leskela, Andrew McGinley, Spencer Bergman, Nick Olson, and finally, me, Tyler Schuman, are going to be talking about the many different steps that we had to take to finally end up with a working boat. This project definitely wasn't the smoothest, as there were some problems that we had to address. So hold on tight as you are about to enter the splash zone. All right. In this presentation, we will be talking about numerous different things, including our entire design process from start to finish. We will also be sharing each of our individual concept designs and the thought that went into each of them. Finally, there were a few issues that we faced along the way during this project, so we will be discussing exactly what those problems were and how we managed to overcome them to get a final product. To start off with this long and vigorous project, we first have to take a look at the engineering design process. This process is a series of different steps that engineers, such as us, take in order to find a solution to any given problem. The first step is to define the problem at hand. This is arguably the most important step because if you don't know exactly what the problem is, then you can't get an appropriate solution. Once that is figured out, the next step would be to brainstorm some possible solutions and then do research on those found solutions. Brainstorming is very important because there can be multiple solutions to one problem, and the more ideas you have, then the more solutions can be produced. Next, one would want to narrow down all of the ideas that were thought of and then create a final plan based on what would best solve the problem. The fifth step of the engineering design process is to create a prototype. This will allow engineers to be able to take a hypothetical solution at hand to an actual physical prototype. The final steps would be to test the prototype to see if it solves the initial problem, and then improve and change the prototype depending on the outcome of the tests. The engineering design process is a very helpful tool that engineers use every day to solve difficult problems. So, what exactly are we trying to accomplish with this project? First and most importantly, we are trying to create a boat that is powered by a 4-bar mechanism. For our boat, we want it to obviously float, to be able to go in a straight line, and to be relatively quick compared to our competition. With our 4-bar mechanism, we wanted it to be simple, work efficiently, and stay intact and not break while it's running. If all of these things happen, then we will be very successful with our goal of creating an impressive boat.
Our constraints are the boat had to fit within a 7 by 7 by 12-inch box and needed to include a 4-bar mechanism that would contribute to the motion output. In the beginning of the design process, we each researched how to effectively solve the problem. We researched the hull design that would affect stability and straightness. We also researched propulsion types and how a 4-bar mechanism could be incorporated. We shared our research with each other before starting the design process. In the design process, we each modeled our own boats in SolidWorks. The first boat design is by myself, Ryan Leskela. My hull design was to use a pontoon-style hull because of the increased stability. My 4-bar mechanism attaches the motor to the rudder to steer the boat in a sense, but we are unsure if this design would work in the intended manner.
Alright, moving on to design 2. This was done by Spencer Bergman, currently talking to you right now. I wanted to use a design similar to the World War II landing crafts that can be seen on the beaches of Normandy. I thought this design would be perfect for flotation and also trudging through the upstream backward force acting upon us because we need to disrupt the upstream force in a way that's not pushing the boat back at a conservative amount. Then, moving on to the 4-bar mechanism, is a parallelogram linkage system in which points A and D are fixed. Point D is the battery, and point A is a rod that is holding down the water wheel that is connected to the boat itself. So that point is also fixed. Then link 2 is the water wheel itself. I thought it was pretty redundant to create another link and then connect that link to the water wheel. So that is why I consider the water wheel itself as link 2 to, one, provide proficiency and less parts to print, which takes more time. That will be all for design 2, and you will be moving on to design 3 to be looking at design 3.
So my design consisted of kind of like a pontoon type design that you'd see out on the lake in the summer, but I used 2 full keels like a sailboat would to help it keep straight so it would track better. I also used a 4-bar in the motor on an angle to drive a prop because I thought that'd be more efficient than a water wheel until our professor said that we should probably use a water wheel because it'll make it easier, which is what we ended up doing.
Next up is design number 4. This was made by me, Tyler Schuman, and I decided to go with a pontoon style boat as they are relatively wide and stable compared to other boats. I figured that if I went with this design, then there would be little to no chance of the boat sinking, and that hopefully the boat would go more straight compared to a very narrow boat. Next, for my 4-bar mechanism, I had joint A and D grounded to the boat. I then attached the motor and a paddle to link C in hopes for the mechanism to create a sort of push-pull motion. I wanted the motion to be similar to oar boats or even the movement that kayaks make while rowing.
My design is all about speed. I decided to go with a wedge shape to reduce drag, but realized this likely wouldn't be very stable or go very straight. To solve both of these problems, I added 3 fins off the back. The shape of the fins would ensure that the boat would go straight, and the outer fins could be weighted to increase stability. The boat would be driven by a propeller. In other boat designs I looked at, the shaft driving the propeller would go through the hull of the boat, requiring a gasket. I used 2 parallelogram 4-bar mechanisms to transfer the motion over the back side of the boat rather than through it.
When it came to grading our boat's functionality, we based it on 5 different categories. One was whether they're lightweight, other was floating, other if it goes forwards, and another aesthetics, and then the last one was if it was within the constraints of what we were set to. So 3 of our boats came out as a tie, and the other 2 kind of came up in the end. But when we actually came to finalizing a design, we kind of took all 3 of the top winners and we kind of pushed them into one, and that is how we ended up coming up with our final boat.
So for picking the best design, we actually did not pick a certain individual's set design. Instead, as a group, we agreed on key fundamentals from other groups. For example, from design 4, we like the pontoon style idea of the shape of the bottom shape of the hull because we agreed that it would provide some water current to go through the middle, which would not provide a great force when we're trying to push it upstream because the upstream water would just pass right through the middle without creating a larger scale force if we used a solid hull. Then moving on, we used designs 3 usage of a water wheel because we thought a water wheel would provide consistent force acting through the water itself without causing the boat to shift from left to right if we used a paddle system or a rowing type system because that was not a constant force acting through the water because you're going in and out. And then for the hull itself, we agreed that design 1 was a perfect design to use for a hull because it had a hollow interior in which we could mount the battery and the 4-bar mechanism itself to the ship without having any top-heavy weight acting upon it. Then it should also be noted that in this design we implemented gears. That way we can have 2 4-bars acting on both sides of the water wheel. That way we provide a constant force acting upon it. not acting upon the forebar, which wouldn't cause it from switching from crossed to parallel. Now that the design process has been discussed, we should now discuss how we brought our boat idea to life in itself. As a group, we kind of decided that we wanted to 3D print the hull itself. One of the issues we did arise from this when we first started was the 3D printers could not handle the scale of our boat, so we decided to cut the boat in half and print out 2 halves. And the 3D printers did have an issue at first in which both hulls ended up being rough edges. But after getting a different 3D printer, this process was solved and all the edges were smooth with no rough edges or any noticeable sticking out parts. Then for the bolts and nuts itself, we decided to use metal bolts for the joints, and then the nuts were to hold down the bolts itself so they don't become unscrewed from the hull itself. That is how we designed our hull and how we also print out our hull. We will be moving on to the next slide after this. We are still on the assembly part of the boat. As you know, on our last slide, we did have to 3D print our hull into 2 halves. Because of this, we did have to super glue both the halves together. We did super glue it. I think we put on 3 layers to be safe that the hull wouldn't split in half and sink our boat and no longer work. At first, after the glue dried, we did test it. We put it in the water. It did float, but we realized that our boat's going to have weight on it with the battery and the motor itself. So we put all the motor assembly onto the boat, and then we also put batteries inside the boat, as you can see in this picture. And one of the things we noticed is if our battery pack was towards the front of the hull, it's going to become forward heavy, which potentially could take on water. So we realized and put the battery pack towards the end of the hull. That way it's back heavy, and if we needed any more weight, we could put more weight in the front, but that did not occur. This is it for that slide, and we will be moving on to the next one. The next thing was assembling the drivetrain itself and the 4-bar mechanism, the motor, the batteries, the water wheel, and the 4-bar mechanisms. We did have a group meeting on 4/9 to assemble and test our mechanism. Originally, our design, we didn't have 2 4-bar mechanisms, as you saw on a few slides back. And what we noticed is when we ran our 4-bar mechanisms, it would start off in parallel and then it'd switch to cross. So the water wheel would have a forwards and backwards motion, which would not propel the boat forward. It just had the boat stuck in limbo. So as a group, we agreed that something needed to be done in order to correct our mistake. And after we assembled everything, we talked over as a group, and we did decide on a new design. As you saw 3 slides back, that is our final design. There were some other issues, but those issues will be addressed on the next slide. As I briefly discussed before, our boat, when we originally assembled it, did have some issues. One of them being, like I said on the last slide, the 4-bar mechanism did not work. It was going from parallel to cross, so the water wheel was basically in limbo from going forwards to backwards. And if we kept this design, the boat would not be propelled forward and would not be able to go upstream. And then one of the issues we did have was assembling the motor. At first, the motor did not work correctly at first. It was getting locked up. To solve this issue, we did apply some grease on the gears, and after that, it still wasn't working, but we realized that we put too much grease on the gears, so we had to wipe off some grease, reassemble it, and the battery and motor itself did finally work. I did mention this on a few slides back. Some of the 3D printers were not working correctly, and there was minimum availability. So there was some issues where we had to reprint some things due to 3D printers not working, and we also were rushed a little bit on time, so we couldn't get some more design aesthetics in due to the minimum availability of the 3D printers itself. That is all the issues that seem to occur. in our problem that we had with the boat. We will be moving on to the next slide after this.
So since our design didn't work the way that we wanted it to, and we couldn't keep a continuous rotational motion, we had to come up with another way of how to do this. So we went and looked at the example that you had in your office, and we saw that they used 2 4-bars, kind of a design like that, so that it would keep pushing it through while it's on the next rotation. So we ended up coming up with a gear train that used 2 gears and a 4-bar on each side offset by 90 degrees, so that when one was at the top of its revolution, it could push the other through next, and we could have continuous rotation. After we re-engineered our boat and we added the 4-bar and our gear train in, we then played around with settings in the motor and gear ratios of how fast we wanted it to go. This video here shows us testing it as a group and trying to see what setting works the best and making sure that it was continuous and reliable rotation.
Our 4-bar mechanism is a parallelogram or change point mechanism. We use this mechanism to transfer the rotation at point A to point D. Links 1 and 3 are 2.39 inches long, links 2 and 4 are 1/2 inch long. The motor axle at point A is a 1/4 inch higher than the axle of the water wheel at point D, and these axles are 2.38 inches apart horizontally. Using the tachometers in the fluids lab, we found that our motor ran at 930 RPM when connected to the 4-bar mechanism. We were tasked with finding the angular velocity and angular acceleration of each link. To find these values, we started with velocity analysis. First, we listed the known relationships of motion. Points A and D have no velocity as they are anchored to the boat. Because the mechanism is a change point mechanism, it is known that points B and C will have the same velocity, and that the angular velocity of links AB and CD will be the same. I will be referring to the links by the names of their endpoints, rather than their numbers for the remainder of the calculations. As seen in the diagram on the previous slide, link 1 is link AD, link 2 is link AB, link 3 is link BC, and link 4 is link CD. Calculations begin with link AB. Knowing the velocity at A, an equation was written to calculate the velocity of B. The relationship used here is that the velocity of B is equal to the velocity of A plus the cross product of the angular velocity of link AB and the radius from A to B. This equation can be expanded to show the 3D components of each vector, substituting for VA, 0 for VA at the same time. After completing the cross product, the x components of each vector can be set equal to each other, as can the y components. These equations can then be used to find VB, and due to the fact that VB is equal to VC, VC is also known. Next, in the velocity analysis, we focused on link BC. Using the same relationship as the previous link, VC is set equal to VB plus the cross product of the link's angular velocity and the radius from B to C. Leveraging the known relationship of the change point mechanism, VC equals VB, VC and VB can be cancelled, leaving 0 equal to the cross product. Knowing that the radius is not 0, the angular velocity must be 0. Completing the velocity analysis, the angular velocity of link BC is 0. The velocity of B and C is 48.69 inches per second, and the angular velocity of links AB and CD is 97.39 radians per second. With the velocity analysis complete, we moved on to the acceleration analysis. The known relationships of motion here are: due to constant RPM, the angular acceleration of link AB is 0. Points A and D grounded to the boat, will have no acceleration, and the angular velocities from the velocity analysis. Starting again with link AB, and knowing acceleration of A, acceleration of B is solved for. The relationship used here is that the acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A. The acceleration of B with respect to A is equal to the cross product of the angular acceleration of link AB and the radius from A to B minus the radius from A to B times the square of the angular velocity. Again, the equation is expanded into its vector components, and these components are set equal to each other, substituting 0 where appropriate to reduce the complexity of each equation. This leaves us with the acceleration of B in the x direction equal to 0, and acceleration of B in the y direction equal to negative radius from A to B times the square of angular velocity. Next, link CD is analyzed to find the equations for acceleration at C. The same relative acceleration relationship is used again, this time with having known motion at D and solving for acceleration at C. Following the same steps as the previous link, we arrive at the equations for acceleration at C. In completing these calculations, it could have been assumed that angular acceleration of link CD was equal to angular acceleration of link AB, which is equal to 0, using the relationships of the change point mechanism. This would have removed the need to analyze link BC to find acceleration of C in the x direction. Unfortunately, this relationship was not recognized, and the calculations were completed along an alternate path. This left us with acceleration of C in the x direction equal to negative radius from D to C times the angular acceleration, and acceleration of C in the y direction equal to negative radius from D to C times the square of angular velocity. Moving on to link BC, the relative acceleration relationship returns. The vectors are expanded, and a second set of equations for acceleration at C are written. With a similar relationship as used for link BC in the velocity analysis, acceleration of C is equal to acceleration of B. The equation of y components can be reduced to 0 equals radius times angular acceleration. Again, knowing radius is not 0, angular acceleration of link BC must be 0. This, finally, is substituted into the x-component equation and gives us the expected relationship that acceleration of C in the x direction is equal to acceleration of B in the x direction. With the calculations completed, velocity and acceleration is known at each point, and angular velocity and acceleration is known for each link. Angular velocity for link BC is equal to 0. Velocity of point B is equal to 48.69 inches per second to the left. Angular acceleration of link BC is equal to 0. Acceleration of point B is equal to 4,742.4 inches per second squared down. Angular velocity of link CD is equal to 97.39 radians per second counterclockwise. Velocity of point C is equal to 48.69 inches per second to the left. Angular acceleration of link CD is equal to 0. Acceleration of point C is equal to 4,742.4 inches per second squared down. This concludes the theoretical kinematic study.
The kinematic study in SOLIDWORKS yielded the following results, which match the theoretical results found in the first method. When testing the final product, it does not go straight. Possible causes of this is the boat is heavier on one side than it is on the other, making the drag coefficient not symmetrical, causing it to turn.
So overall, I'd like to say that our boat was a success because we completed both the tests and it went upstream and downstream. There were a few things though that kind of set us back. One was picking the boat that we actually wanted because we had obviously 5 different designs and we kind of tried to incorporate them all into our final boat. Another thing that went bad was our first 4-bar mechanism didn't work and we had to go back to the drawing board because of it, and it took an extra, I'd probably say 4 or 5 days to get it up and running, so it was kind of a time crunch. A few things that went well was our first boat design that we made. It floated and 3D printed nicely, so everything there worked out well. And also another thing that made this project a lot more bearable and a lot easier than maybe some other groups was that all of our team members seemed to get along and we all worked well with each other. I know I was the group leader, but everybody pulled their load and did their part, and everybody had their strengths and their weaknesses, and we all kind of fit together really good, and I think that is a big part of why our boat actually worked. But other than that, yeah, it was a success for sure.